In 1956, researchers gathered at the Dartmouth Summer Research Project on Artificial Intelligence, where the term artificial intelligence first gained scientific momentum. At that time, global computing power was less than 0.000001% of today's capacity. Yet the vision was bold: machines that could reason like humans. Decades later, this early meeting would be remembered as the first step toward the idea now called artificial general intelligence. However, progress was slow. By the 1980s, AI funding had already experienced two major AI winters. Investment dropped by more than 70% in some research programs. Meanwhile, computers still struggled with simple tasks like speech recognition. Nevertheless, the dream of AGI survived inside universities and labs. Researchers quietly continued building algorithms, believing that exponential growth in computing would eventually unlock a breakthrough. Then the Internet era arrived. By 2000, global Internet users surpassed 400 million, generating massive digital data. This changed everything. Machine learning models now had something they previously lacked: scale. As data centers expanded and GPUs became widely used, AI research accelerated. Consequently, companies realized that the path to AGI might depend not only on algorithms, but also on massive datasets and computing infrastructure. A turning point appeared in 2012. At the ImageNet Large-Scale Visual Recognition Challenge, a neural network dramatically reduced image recognition errors from 26% to about 15%. The model, called AlexNet, used GPU computing to process millions of images. This single breakthrough convinced technology leaders that deep learning could outperform traditional software methods, igniting a new global AI investment wave. Following that success, technology companies rapidly expanded AI research divisions. By 2016, the global AI market was valued near $3 billion. Yet forecasts predicted growth above $190 billion by 2025. As a result, firms like Google, Microsoft, and Amazon began hiring thousands of researchers. Quietly, the objective behind these investments was not just better software, but the long-term pursuit of AGI. Meanwhile, breakthroughs continued. In 2016, a program from DeepMind defeated world champion Lee Sedol in the complex board game Go. The system, called AlphaGo, won 4 out of 5 matches. Go has about 10 to the power of 170 possible board states, more than atoms in the observable universe. Consequently, many scientists saw this as evidence that machines could master extremely complex decision spaces. As a result, investment surged. Between 2016 and 2020, global private funding in AI exceeded $90 billion. Venture capital alone grew more than fivefold in just 5 years. Governments also joined the race, with national AI strategies announced in over 60 countries. Therefore, the pursuit of AGI slowly transformed from a research ambition into a global technological competition. At the same time, computing power expanded dramatically. According to several AI studies, the amount of compute used in the largest training runs grew more than 300,000 times between 2012 and 2018. Massive data centers built by companies like NVIDIA partners and cloud providers became critical infrastructure. Consequently, whoever controlled the most compute resources gained a major advantage in the AGI race. Then language models changed the landscape. In 2018, researchers at OpenAI introduced the transformer-based model family beginning with GPT architectures. These systems learn patterns from billions of words across the internet. By scaling parameters from millions to hundreds of billions, performance improved rapidly, suggesting that larger models might approach more general intelligence capabilities. Finally, in 2022, the public experienced large-scale AI directly through ChatGPT. Within 5 days, the system gained over 1 million users. 2 months later, it surpassed 100 million users, becoming one of the fastest-growing consumer technologies in history. Consequently, global awareness of AI surged, and companies realized that the path toward AGI could reshape entire industries. Consequently, competition intensified. By 2023, more than $50 billion had been invested globally in generative AI startups in a single year. Major firms expanded research budgets rapidly. For example, Microsoft committed multi-billion-dollar investments into OpenAI to accelerate large model development. This partnership allowed access to massive cloud infrastructure, signaling that AGI development would depend heavily on industrial-scale computing resources. Meanwhile, compute demand surged dramatically. Training some advanced models required tens of thousands of GPUs operating for weeks. A single modern AI training run can cost between $10 million and $100 million depending on model size. Consequently, companies building AGI systems began constructing enormous data centers capable of delivering exaflop-scale performance to train increasingly complex neural networks. At the same time, data volumes expanded across the world. By 2024, global digital data creation exceeded 120 zettabytes annually, compared with only 2 zettabytes in 2010. Social media posts, scientific papers, videos, and code repositories became training material for AI systems. Therefore, the Internet itself gradually evolved into one of the largest knowledge sources used to train models aiming for general intelligence. However, companies realized that data alone was not enough. Algorithmic innovations also mattered. The transformer architecture introduced attention mechanisms that allowed models to understand relationships between words, images, and code more effectively. As a result, performance benchmarks improved rapidly across translation, reasoning, and programming tasks, suggesting progress toward broader intelligence capabilities. Therefore, AGI increasingly appeared not as a distant theory but as a potential technological milestone. Analysts estimated that global spending on AI infrastructure, including chips and data centers, could exceed $300 billion by the end of the decade. Consequently, the race for AGI transformed into one of the largest industrial investments in modern technological history. Meanwhile, specialized hardware became essential. Graphics processors from NVIDIA evolved into the backbone of AI computing. By 2024, more than 80% of AI training workloads globally relied on these chips. A single modern AI cluster could contain over 20,000 GPUs working together. Consequently, semiconductor supply chains became a strategic factor in the race toward artificial general intelligence. At the same time, cloud infrastructure expanded rapidly. Providers such as Amazon Web Services, Google Cloud, and Microsoft Azure began building hyperscale data centers worldwide. Some facilities consume over 100 megawatts of electricity, roughly the power usage of a small city. Therefore, the pursuit of AGI increasingly depended on energy, cooling systems, and global network infrastructure. Meanwhile, research teams continued scaling models. In 2018, many language models had fewer than 1 billion parameters. By 2023, some exceeded 500 billion parameters. Studies showed that performance improved predictably as model size, data, and compute increased. Consequently, scientists began to view scaling laws as evidence that larger systems might gradually approach more general reasoning abilities. However, competition extended beyond companies. Governments also recognized the strategic importance of AI leadership. By 2023, more than 70 countries had released national AI strategies, collectively investing tens of billions of dollars. These policies aim to expand research institutions, attract global talent, and build advanced computing infrastructure capable of supporting next-generation AI development. Therefore, the pursuit of AGI gradually evolved into a global technological race involving corporations, universities, and governments simultaneously. Analysts estimated that the broader AI economy could contribute over $15 trillion to global GDP by 2030. Consequently, the stakes grew far beyond software innovation, shaping economic policy, national security strategies, and the future structure of the digital world. Meanwhile, the hardware race intensified. In 2023, the most advanced AI chips produced by NVIDIA contained over 80 billion transistors each. Large training clusters could combine thousands of these chips, delivering more than an exaflop of computing power. Consequently, a single AGI-scale training run might involve millions of GPU hours, making raw computational capability one of the most decisive advantages in the field. At the same time, talent became another critical resource. By 2024, estimates suggested fewer than 25,000 researchers worldwide had deep expertise in advanced machine learning systems. Yet technology companies competed aggressively for these experts, offering compensation packages exceeding $1 million annually in some cases. Therefore, the race for AGI increasingly resembled a global competition not only for machines, but also for rare scientific talent. Meanwhile, AI systems expanded beyond language. Models began combining text, images, audio, and video into unified architectures known as multimodal systems. These models could analyze photographs, generate code, describe videos, and answer questions simultaneously. Consequently, researchers believe that integrating multiple sensory inputs might move machines closer to human-like reasoning and broader problem-solving capabilities. In parallel, AI applications spread rapidly across industries. By 2024, more than 35% of global companies reported using AI tools in at least one business function. Finance used AI for fraud detection, healthcare for medical imaging analysis, and logistics for supply chain optimization. Therefore, organizations began viewing AI not just as a research topic but as a central driver of productivity and economic growth. Consequently, expectations around AGI continued to grow. Some analysts predicted that if general-purpose AI systems automate a large portion of knowledge work, global productivity could increase by 1 to 2% annually for decades. Such growth would be comparable to the economic impact of the Industrial Revolution. Therefore, the vision of AGI increasingly shaped long-term strategies across the entire technology sector. Meanwhile, energy requirements became a serious constraint. Large AI data centers often consume 50 to 150 megawatts of electricity. Some facilities planned for the late 2020s are expected to exceed 300 megawatts. Consequently, companies pursuing artificial general intelligence began investing in renewable power contracts, advanced cooling systems, and high-density server designs to support massive computational demand. At the same time, the cost of training frontier models continued to climb. Early deep learning models in 2012 could be trained for under $50,000. By contrast, some advanced training runs in 2024 were estimated to exceed $100 million. Therefore, only a small number of organizations with large capital reserves could realistically attempt building AGI-scale systems. Meanwhile, corporate alliances expanded. Technology firms increasingly collaborated with research labs and universities to accelerate innovation. For example, partnerships between Microsoft and OpenAI integrated advanced AI models into global cloud services. Consequently, AI research moved from isolated laboratories into large industrial ecosystems supported by vast computational infrastructure. However, rapid progress also raised concerns about safety and control. Some researchers warned that extremely capable AI systems could produce unintended outcomes if poorly aligned with human objectives. Leaders such as Geoffrey Hinton publicly discussed potential risks, urging careful research into alignment and governance before deploying increasingly powerful models. Therefore, new research fields emerged alongside AI development. One growing area, often called AI safety, focuses on ensuring that advanced systems behave reliably and transparently. Organizations such as Anthropic and several academic groups now dedicate significant resources to studying alignment, interpretability, and responsible deployment as progress toward AGI accelerates. Meanwhile, researchers examined how rapidly AI capability had been improving. Studies showed that the computational power used in the largest AI training runs had doubled roughly every 3 to 4 months between 2012 and 2018. This growth was far faster than the traditional pace described by Moore's law. Consequently, progress toward more advanced AI systems accelerated at a historically unusual rate. At the same time, companies expanded the scale of their research teams. By 2024, several leading technology firms employed thousands of engineers working directly on AI systems. For example, Google integrated AI research across many divisions, from search to robotics. Therefore, the pursuit of advanced intelligence gradually became embedded across nearly every major product line. Meanwhile, the semiconductor industry adapted to meet AI demand. Specialized AI accelerators and tensor processing units were developed to handle large neural networks more efficiently. Chips designed specifically for machine learning tasks could deliver several times the performance of traditional processors. Consequently, hardware innovation became tightly linked with progress in artificial intelligence research. In parallel, AI models began assisting scientists in complex research. Systems trained on large scientific datasets started helping analyze chemical compounds, protein structures, and astronomical observations. Consequently, researchers estimated that AI-assisted discovery could reduce some experimental timelines from years to months, significantly accelerating progress across multiple scientific disciplines. Therefore, the vision of AGI increasingly expanded beyond automation. Many experts argued that general-purpose AI could function as a universal research assistant capable of analyzing enormous volumes of knowledge. If achieved, such systems might accelerate innovation across medicine, climate science, engineering, and space exploration, reshaping how humanity approaches scientific discovery. Meanwhile, the economic scale of AI continued expanding. By 2024, global corporate spending on artificial intelligence technologies exceeded $150 billion annually. Market analysts projected that this number could surpass $1 trillion by the early 2030s. Consequently, the pursuit of artificial general intelligence increasingly became one of the largest technological investments in modern economic history. At the same time, productivity studies began measuring AI's impact. Research suggested that workers using AI-assisted tools could complete certain knowledge tasks 30% to 50% faster. Software developers using advanced coding assistants sometimes reduced development time by nearly half. Therefore, companies recognized that more powerful AI systems could dramatically transform how intellectual labor is performed. Meanwhile, language models grew more capable of reasoning across domains. Some modern systems could answer questions about mathematics, history, programming, and law within the same interface. This cross-domain capability resembled early signs of general intelligence. Consequently, researchers increasingly focused on building architectures capable of learning many skills simultaneously rather than specializing in a single task. However, building such systems required enormous datasets. Estimates suggested that large models were trained on hundreds of billions of words and millions of images. Data pipelines collected information from books, research articles, and public web pages. Therefore, managing data quality, filtering harmful content, and maintaining privacy protections became essential challenges in large-scale AI development. Consequently, the AGI race gradually shifted from experimentation to infrastructure building. Companies constructed vast AI supercomputers designed specifically for training massive models. Some clusters contain tens of thousands of GPUs connected by high-speed networks. These systems formed the computational foundation upon which researchers hope to develop machines capable of general reasoning. Meanwhile, investment in AI startups surged. In 2023 alone, global venture capital funding in AI exceeded $50 billion, a 70% increase from the previous year. Startups focused on natural language processing, robotics, and multimodal AI attracted attention from major corporations. Consequently, companies not only developed in-house projects but also acquired promising firms to accelerate progress toward AGI. At the same time, regulatory attention increased. Governments and international bodies began drafting AI safety and governance guidelines. For instance, the European Union proposed regulations targeting high-risk AI applications. Therefore, companies pursuing AGI had to consider ethical, legal, and societal implications alongside technical performance, adding complexity to the global race. Meanwhile, cloud computing became a strategic enabler. Providers like Microsoft Azure and Amazon Web Services offered elastic access to thousands of GPUs. This allowed even smaller organizations to train advanced models. Consequently, the race toward AGI became partially democratized, though major players still controlled the largest infrastructure and datasets. At the same time, algorithmic efficiency improved. Techniques such as sparsity, quantization, and model pruning reduced compute requirements while maintaining performance. Researchers discovered that optimizing architecture often mattered as much as raw scale. Therefore, the pursuit of AGI became a balance between building bigger models and designing smarter, more efficient algorithms. Consequently, AGI research increasingly focused on multi-agent and self-improving systems. Experiments with reinforcement learning demonstrated that AI could learn through simulated interactions, adapting strategies over time. Analysts projected that these capabilities, combined with vast computation and data, might form the foundation for systems capable of generalized intelligence beyond narrow tasks. Meanwhile, AI ethics emerged as a crucial area of study. As models became more capable, incidents of bias and unintended outputs increased. For example, some language models misrepresented minority groups in training data. Consequently, companies like Anthropic and OpenAI invested in alignment research to ensure future AGI systems behave reliably and safely. At the same time, education shifted to meet AI demand. By 2024, universities worldwide had created specialized AI programs, producing thousands of graduates annually. Tech giants actively recruited these students, offering salaries far above industry averages. Therefore, human capital became as critical as compute and data in the global effort toward AGI. Meanwhile, multimodal AI demonstrated rapid progress. Systems could analyze images, generate text, and answer questions in combination. For instance, models could describe videos, write code, and summarize research papers simultaneously. Consequently, researchers saw this as a practical step toward generalized intelligence that operates across multiple cognitive domains. At the same time, AI began automating scientific discovery. Algorithms helped design new molecules, predict protein folding, and simulate chemical reactions. Some studies estimated that AI-assisted research could reduce drug development timelines by up to 50%. Therefore, organizations recognized that AGI could act not only as a tool but as a transformative accelerator for human knowledge. Consequently, the AGI race became a central strategic priority for major companies. Analysts estimated that AI-driven automation could increase global GDP by trillions of dollars over the next decade. Thus, investment, research, talent acquisition, and infrastructure development all converged on a single long-term objective: building machines capable of general intelligence across domains. Meanwhile, AI's scalability challenges grew more complex. Training models with hundreds of billions of parameters required petabytes of storage and extremely high-speed interconnects between GPUs. Data movement became a bottleneck, forcing engineers to redesign memory hierarchies and network topologies. Consequently, solving infrastructure efficiency became as crucial as algorithmic innovation in the AGI race. At the same time, collaboration between academia and industry intensified. Research labs at universities began publishing foundational work, while corporations offered access to large-scale compute. For example, Google DeepMind partnered with academic institutions to explore reinforcement learning at scale. Therefore, the boundaries between academic theory and industrial practice blurred, accelerating progress toward AGI. Meanwhile, AI began tackling real-world problems. Financial institutions used models for fraud detection and portfolio optimization, while logistics firms predicted supply chain disruptions. Studies estimated that AI could improve operational efficiency by up to 40% in certain industries. Consequently, the economic incentives for developing AGI became clearer, as broader intelligence could exponentially expand such benefits. At the same time, governments recognized the strategic importance of AI leadership. National policies in countries like China, the United States, and the European Union included multi-billion-dollar investments in AI research and supercomputing. Analysts projected that global competition for technological dominance could influence economic growth and national security. Therefore, AGI became a geopolitical as well as corporate priority. Consequently, research focus shifted toward generalization. Models were trained not just for specific tasks but to adapt to new challenges without retraining. Techniques like few-shot and zero-shot learning became central. Researchers believed that these capabilities could be the first measurable steps toward true general intelligence, linking advances in model architecture, data, and compute into a coherent path forward. Meanwhile, open-source AI initiatives expanded rapidly. Frameworks like TensorFlow and PyTorch enabled millions of developers worldwide to experiment with advanced models. By 2024, hundreds of open-source large language models were publicly available. Consequently, knowledge dissemination accelerated, allowing even smaller organizations to contribute to the collective understanding needed for AGI development. At the same time, AI began impacting creative industries. Systems generated art, music, and writing with increasing sophistication. Some estimates suggested AI-generated content could account for over 20% of digital media creation by 2030. Therefore, companies recognized that AGI could extend beyond analytical tasks, potentially automating creative problem-solving at scale. Meanwhile, research and reinforcement learning advanced. AI agents learned to navigate complex simulated environments, improving through trial and error. By 2023, some systems could outperform humans in virtual strategy games with millions of possible states. Consequently, reinforcement learning became a key tool for developing systems capable of adaptive, generalized decision-making. At the same time, hybrid models combining symbolic reasoning with deep learning emerged. These systems could handle abstract logic alongside statistical pattern recognition. Studies showed improved performance in tasks requiring reasoning, planning, and problem-solving. Therefore, integrating multiple AI paradigms became a critical strategy in moving closer to AGI-level intelligence. Consequently, the AI research ecosystem matured into a multidimensional race. Companies now coordinated compute, data, algorithms, talent, and safety research simultaneously. Analysts projected that the first organization capable of combining these elements effectively could achieve unprecedented advantage in both technology and market influence, reinforcing AGI as the ultimate long-term objective. Meanwhile, AI governance discussions intensified. By 2024, over 50 policy papers addressed AI safety, ethical deployment, and alignment. Some governments proposed licensing advanced AI models to mitigate risks. Consequently, companies pursuing AGI had to balance rapid development with compliance and ethical responsibility, making regulation an integral factor in strategic planning. At the same time, cross-industry partnerships flourished. Pharmaceutical, automotive, and energy sectors collaborated with AI labs to integrate intelligence into operations. Analysts estimated that such partnerships could accelerate innovation cycles by 2 to 3 years per sector. Therefore, AGI was increasingly seen as a unifying tool across industries rather than a purely computational goal. Meanwhile, AI benchmarks evolved. Traditional accuracy metrics were supplemented with reasoning, multitask performance, and adaptability tests. Some models were evaluated on dozens of tasks simultaneously to measure generalization. Consequently, researchers could quantify progress toward AGI more systematically, identifying strengths and weaknesses across domains. At the same time, compute optimization became a research priority. Techniques such as distributed training, model parallelism, and hardware-aware scheduling reduced resource consumption by up to 50%. As energy and cost constraints grew, efficient infrastructure planning became crucial. Therefore, scaling laws were paired with optimization strategies to make AGI development feasible. Consequently, AGI's strategy evolved into a holistic challenge. Success depended not only on algorithmic breakthroughs but also on integrating massive compute, multi-domain data, talent, safety research, and regulatory compliance. Analysts argued that these combined factors defined the competitive landscape, explaining why top companies aggressively prioritized AGI as a central goal. Meanwhile, AI-driven automation reshaped labor markets. By 2024, reports estimated that 30 to 40% of repetitive knowledge tasks could be partially automated with current AI tools. Companies observed reductions in time spent on data analysis, coding, and report generation. Consequently, the promise of AGI extended beyond efficiency. It represented a potential redefinition of workforce productivity on a global scale. At the same time, AI began improving human decision-making. Systems provided predictive analytics in finance, medicine, and logistics, often outperforming human experts in specific domains. Studies suggested error reduction by up to 60% in certain tasks. Therefore, top companies increasingly viewed AGI as a tool to augment human cognition across industries, amplifying strategic advantages. Meanwhile, AI models demonstrated emergent reasoning abilities. Large language models could solve multi-step problems, generate code, and perform basic planning. Researchers observed that performance scaled predictably with model size and data. Consequently, scaling alone became a central strategy, with firms investing heavily to create ever larger, more capable systems on the path toward general intelligence. At the same time, data governance became critical. Collecting, cleaning, and labeling trillions of data points required robust pipelines and privacy safeguards. Companies had to manage intellectual property and comply with international regulations. Therefore, the control of high-quality datasets became as strategically important as computing power or algorithms in the race for AGI. Consequently, the race for AGI increasingly resembled a multi-front campaign. Firms invested simultaneously in talent acquisition, compute infrastructure, advanced algorithms, safety research, and regulatory compliance. Analysts projected that the first organization to successfully integrate all these factors would achieve a dominant technological position, reinforcing why AGI became the primary objective for leading companies. Meanwhile, multimodal AI advanced further. Models could interpret text, images, and audio simultaneously, enabling richer interactions. Experiments demonstrated that AI could generate detailed explanations from visual input or summarize complex multimedia content. Consequently, these capabilities signaled that AGI might emerge through systems capable of integrating knowledge across multiple sensory modalities. At the same time, AI-assisted scientific research accelerated. Predictive models helped identify promising chemical compounds, optimize renewable energy systems, and model climate scenarios. Studies suggested AI could reduce experimentation cycles by up to 50%. Therefore, AGI was increasingly viewed not just as a computational milestone but as a transformative enabler of human innovation. Meanwhile, global AI funding continued to grow. By 2024, private and public investments exceeded $200 billion annually, with projections of $500 billion by 2030. Venture capital flowed to startups in generative AI, robotics, and multimodal intelligence. Consequently, AGI research became a top priority not only for technology giants but also for governments and private investors worldwide. At the same time, AI safety research intensified. Techniques such as reinforcement learning with human feedback, RLHF, and interpretability tools became standard practices. Organizations like Anthropic and OpenAI focused on alignment, mitigating risks of harmful outputs. Therefore, safety became inseparable from the pursuit of increasingly capable systems. Consequently, AGI's strategy required coordination across multiple dimensions. Scaling models, acquiring data, optimizing infrastructure, ensuring safety, and adhering to regulations had to occur in parallel. Analysts concluded that the first organization capable of integrating these components effectively would gain both technological dominance and strategic influence, cementing AGI as the central objective for top companies. Meanwhile, AI model interpretability became a priority. Researchers developed tools to visualize decision pathways and track reasoning processes in large neural networks. Studies showed that explainable models reduced errors in high-stakes applications like medicine and finance by 20 to 30%. Consequently, understanding model behavior became essential for both safety and accelerating progress toward AGI. At the same time, international competition intensified. Countries like the United States, China, and members of the EU invested billions in national AI strategies, including supercomputing infrastructure and research funding. Analysts projected that global leadership in AI could determine economic and military advantage for decades. Therefore, AGI became not only a corporate goal but also a geopolitical imperative. Meanwhile, hybrid AI systems emerged. Researchers combined symbolic reasoning with neural networks to enhance logical problem-solving. Experiments demonstrated improved performance in multi-step reasoning and planning tasks. Consequently, integrating diverse AI paradigms became a central strategy to approach generalized intelligence beyond purely statistical learning. At the same time, AI adoption spread across sectors. By 2024, over 40% of Fortune 500 companies used AI in core operations, including predictive analytics, customer service, and supply chain management. Studies projected that early AI adopters could achieve productivity gains up to 50%. Therefore, the economic incentive for AGI grew alongside technological and strategic motivations. Consequently, the pursuit of AGI represents the convergence of compute, data, talent, infrastructure, safety research, and economic strategy. Analysts predict that systems capable of general intelligence could transform industries, accelerate scientific discovery, and redefine global competitiveness. Therefore, leading companies prioritize AGI as the ultimate long-term objective, linking innovation, strategy, and societal impact in a single vision. In conclusion, the journey toward AGI reflects decades of research, massive investments, and global competition. From early AI experiments to today's multimodal and large-scale models, every step has brought humanity closer to machines capable of general intelligence. As this story continues to unfold, stay informed and witness the next breakthroughs firsthand. Subscribe to Best AI today to follow the future of AI, innovations, and the race for AGI.